In Algebra 2, you studied complex numbers. And I'm going to flip the page one page over here. And remember, the idea came from when we were studying quadratics. We found out that when we had quadratic equations, that sometimes the graph of a quadratic would cross the axis 2 times and have 2 real zeros. Sometimes the quadratic would only hit the x-axis 1 time. That would also denote that this is actually a double root, or the factor occurred twice. But sometimes the graph of the quadratic never crossed this x-axis at all, so it would look like there were no real zeros. Well, there weren't any real zeros, but there are 2 zeros. There are 2 numbers that can be plugged in to the quadratic equation for a graph that looks like this and get 0. However, we have to incorporate the number I. So that was where the I came up when you were in Algebra 2. So back to the other page. So we remember that the definition of I was the square root of -1, and that came about when you were using quadratic formula. And I'm going to actually move down to the very bottom question for just a second and look at where you remember this coming about initially. So at the bottom, number 4, when we had a quadratic that was 2x squared plus 5x plus 4, initially when you were studying Algebra 2, you had quadratics that crossed the axis twice, and so you had the quadratic formula that you would use to solve a quadratic equation, and you would find that when you used quadratic formula to solve an equation like so, you got stuck initially and said, whoa, a negative underneath the radical under the discriminant? We can't have that. Well, we changed our understanding of mathematics when we allowed this to occur and had the square root of -1 be defined as I. So now this became a valid solution as long as we were allowing complex numbers to be used. We know graphically this solution will not cross the x-axis. However, it is a viable solution in the world of complex numbers. So when I have an equation like so, and I'm trying to find what are the solutions for this, because it's degree 2, this will have 2 solutions as long as I'm allowed to use complex numbers. And so remember, we use quadratic formula, and we put the values into a plus bi form. Now, if this question had been asked differently, and had been asked for you to factor this quadratic as opposed to solving this quadratic equation, the factorization of this 2x squared plus 5x plus 4 would still require us to use the quadratic formula to find the zeros of that quadratic. And then if I asked you just to factor that quadratic, I would write down x minus the first 0, which comes from using the addition sign between the a plus bi part, and x minus the second 0 to find the other factor. Now, the product of x minus the first 0 times x minus the second 0 doesn't give me the 2 lead coefficient that would have been in the original factored form. So I do have to additionally add on a 2 factor as a multiplier out in front. It takes quite a bit of work to do all the distributing through, but if you multiply this whole thing out, a lot of things will cancel out. Everything with i's will end up canceling out, and when you multiply, and we would end up with 2x squared plus 5x plus 4. Okay, so we had that context back in Algebra 2. Now, a couple other things to remind you of. I'm not going to go through all this on the video, but I reviewed the idea up here in your notes about what we do when we add complex numbers, what we do when we multiply complex numbers. If we have a complex number over a single numerical value, how that denominator goes to both parts of the complex number, and how we factor sum of squares. Remember, with difference of squares can be factored with integers. Difference of squares, like so, a squared minus b squared, that we can factor over the set of integers and not need complex numbers. However, if we have a square plus a square, we're going to need to use complex numbers. You can do the double check on your own to show that if I actually distribute this through, that I'll end up getting a squared plus b squared when I multiply a plus bi times its complex conjugate a minus bi. And there's another term of vocabulary, complex conjugate. These two are complex conjugates. Now, if I asked you to write the square roots of negative 3, so what number squared would equal negative 3? Remember, previously, we would have talked about, well, you can never square a number and get negative 3. That's in the real world. However, if we're allowed to use complex numbers of having an imaginary part I, then it is possible to have this value squared equal negative 3. I did a little bit of the algebra work down here. So we know that there are going to be two numbers, if I'm allowed to use complexity. There are going to be two numbers at work, so x is equal to plus or minus the square root of negative 3. So if I don't use i's, these will be my two solutions. Now, if I use the definition of I as being the square root of negative 1, I can further split up this radical, like so, and then I can break it up into the two parts to arrive at these two solutions. So both of these are square roots of negative 3. I won't go through the details of the next part on 2 and 3. I'll display the answers here and just talk through a couple things on part E. You can see A is adding, C is multiplying, D is squaring some quantity, and E is going through the process of what you do when you have division. And we want this quotient written in a plus bi form. Remember that if you have a complex number divided by a complex number and you want the answer written in a plus bi form, you can't just split this up and do bad math and split this up into like 1/6 over the quotient of these two. That's not algebraically sound. I have to multiply by 1 in a funny form, and I multiply by the complex conjugate. And I showed the algebra that takes place if I do all this multiplication out. And I would end up with this value. And this number 3 example is going back and showing if I have an x squared plus 9, I know anytime I have a square plus a square, or a square plus any number, truthfully this doesn't even necessarily have to be a perfect square, that if you have a binomial where the first term is a square and you're supposed to be breaking it down, and this is an addition sign, I would have to have complex numbers in order to be able to break this down. A subtraction sign, I can break it down over the set of real numbers or integers, but if it's an addition sign, I have to use complex numbers. And this breakdown of having the opposite